Hello, everyone, and welcome to this evening's session. I'm delighted to have as host for this session Dr. Joe Broz, who's recently joined IBM. And in his new role at IBM, Joe's going to be applying his extensive knowledge of quantum technology, business and industry, as well as his government experience to lead a multidisciplinary team across IBM Global Services, IBM Research and IBM Systems to grow the quantum computing business and consulting practice. As I'm sure you're familiar, prior to joining IBM, he was the executive director and chairman of the industry quantum consortium, the QEDC, which was chartered under the National Quantum Initiative Act. He also served as vice president of SRI's International's Advanced Technologies Division, so is ideally placed to moderate this panel on aerospace and defense applications. Joe, I'll hand the floor over to you.
Thank you, Amit. I appreciate the nice introduction, and I really am enjoying the conference, and I'm sure all of our participants have today. It's just terrific. So I'm really pleased to introduce two panelists to speak on our subject today. And I'm going to introduce both of them now at the beginning. They'll each have about 10 or 15 minutes worth of presentations that they'll provide. And then we'll take the remaining time for questions and answers from the audience, as well as I have a few questions that I've prepared for both of these speakers. We're fortunate today to have Zach Dutton with us. Dr. Dutton is a lead scientist and manages the Physical Sciences and Systems business unit within Raytheon BBN. It's a group of over 100 staff and technical individuals who do advanced R&D across several lines of business. And that includes maritime systems, sensors, artificial intelligence, embedded processing, and quantum and photonic technologies. Also, his research has focused on quantum-enhanced optical remote sensing, quantum networks, quantum-limited communication receivers, and he's done quite a lot on quantum computation and superconducting quantum circuits. Dr. Dutton received his BS in physics at UC Berkeley in '96 and his PhD in theoretical physics from Harvard in 2002. Our second panelist today will be Dr. Darren Brock. Dr. Brock is a principal research engineer at Lockheed Martin. He's based in Billerica in Massachusetts. His background is in design, fabrication, and testing of superconductor, molecular, and nanoscale electronics. He led the corporate-wide Lockheed Martin foundational technology thread in quantum technologies, and in that time traveled extensively to the UK, supporting academic partnerships in the quantum hubs programs there. He also spent 2 years as a part-time visiting researcher at the University of Maryland in Chris Monroe's lab. And of course, Chris went on to found IonQ along with Jung-Sung Kim. Dr. Brock currently works research and development projects that support the adoption of quantum tech and advanced classical technologies for both aerospace and defense applications. Both of these speakers are experts and more than adequately qualified to address the topic today, quantum computing in aerospace and defense. I'd like to start first, Dr. Dutton, if you would share your screen and you can go ahead with the slide presentation. And then after that, Dr. Brock will give his slide presentation. So, Zach, I leave it over to you.
Thank you, Joe. Thank you for the nice introduction, and thank you, Amit and team, for the invitation to speak here. I've really enjoyed the conference so far. There's it's touching on a lot of issues that certainly we're dealing with. And are interested in, and I've enjoyed the very open discussion. I was asked, one of the questions I was asked was to at least comment a little bit about what my personal kind of story is, our personal journey. And I think that's relevant because quantum computing has played a very kind of good role in just for me personally. Back when I was doing my PhD, I was in atomic physics. I worked on Bose-Einstein condensation and slow and stopped light. And I went through the kind of, I think what many graduate students do when they have kind of a mid-PhD crisis, where you start to get over the novelty of some of the research you're doing and the experts around the world you're sharing it with, and you start to wonder, who really cares about this, and what's really gonna become of this? Will it ever be used in any way? And around that time, it was kind of realized that some of what I was doing with coherent storage of light was actually a rudimentary quantum memory. And it was like this this light bulb really went off. It really just completely changed my perspective and my motivation to work in the field. And really, since then, I've gravitated more towards quantum technology. And when I joined BBN in 2007, was later acquired by Raytheon, I've worked mostly on quantum technology since then. But as Joe said, I lead a larger group at this point. Physical Sciences and Systems does a number of other things outside of quantum, but quantum has always been kind of my personal interest. So with that, let me tell you a little bit about what we're doing at Raytheon. So this is as you may have heard, Raytheon, what used to be called Raytheon and United Technologies merged just last year. So we now consist of 4 business units: Collins and Pratt & Whitney do a lot of radios, and Pratt & Whitney do a lot of engines, and Raytheon Intelligence and Space and Raytheon Missiles and Defense are kind of the 4 business units that make up Raytheon, this combined Raytheon Technologies company. And where does BBN, where I sit in all that? Well, we actually are technically under Raytheon Intelligence and Space. We certainly do some work with them. But it's worth noting that Raytheon BBN is really an R&D kind of resource across the company. And so what they're really looking to us for are taking things in the lab, taking things that are maybe rather advanced kind of future capabilities being developed at DARPA and other agencies, and really look for ways of transitioning that into their systems of interest. And we excel at that. My particular group that I lead, Physical Sciences and Systems, I think excels at that. In the maritime space, we're bringing a lot of novel technology to the company, and so on and so forth. And quantum and photonics are certainly one of those. And that's what the quantum engineering and computing group that I've been a part of for much of my career belongs to. So I'm going to focus on quantum computing primarily, but I did want to say a few words about kind of how I view the overall quantum technology landscape. You probably heard this from other speakers, but there's kind of the sensing, communications, and computation at a high level. And it's worth noting that while computing is very much of interest, and I think becoming of greater interest, the landscape is much bigger, and perhaps the applications are a little bit nearer term when you expand it into sensing. And so a lot of the work that we're interested in doing as far as technology transition really focuses on things like assured P&T and other things that quantum technologies can give you with respect to quantum advantage in systems. So just to give you an idea of BBN, like I said, we're kind of an advanced R&D firm. We've been around since the 40s, worked in acoustics since the early days. And it's really a company that has, over the decades, had a history of these kind of one-step moves where we, for example, we were very early in acoustics. That led us to eventually be experts in natural language processing. That interest in that natural language processing led us to eventually be experts in machine learning. Our expertise in our kind of needs for acoustic modeling led to expertise eventually in computing and eventually in networking, where we did some of actually the original contract for ARPA that became the ARPANET, that of course became today's internet. And one of those one-box moves was to get into quantum technology. Our networking group looked at an opportunity to bring this new thing called QKD and actually try to see it at metropolitan scale. And so I think this is like a perfect example of how we're able to take something that's in the lab, which QKD was in the lab in the 90s, and really try to make it work at metropolitan scale, where we connected nodes at BBN, Boston University, and Harvard University, and saw a real key being exchanged over a network. Since then, we've got into, of course, quantum computing and superconducting-based quantum computing specifically. And so that's what the Quantum Engineering and Computing Group does. It's about 20 heads. We have expertise in physics, of course, RF engineering and software, work with a variety of CRAD customers, and we've been doing that since about 2001, since that original QKD work, quantum computing since about 2009. We work across, I think, compared to some of the other companies at this conference, we work a fairly broad spectrum of quantum technology, quantum communication, sensing, and computing, as well as some classical technology that uses similar hardware, such as photonic integrated circuits and cryogenic computing. And we build systems, but we're also very much a research group, and we publish in some of the leading scientific journals as well. And so this just kind of gives you a map of some of the areas that the QEC group has had some impact. We're certainly interested in scalable quantum computing technology. I'll focus on that a little bit, but of course, QKD, photonic integrated circuits I mentioned, and cryogenic electronics, as well as several other topics. And there are some capabilities across the broader RTX company that I should say are bring in some very relevant capabilities, especially when we're talking about really scaling this technology up, making it more robust, and packaging it. And those include RF electronics, ASIC design, 3D heterogeneous integration, and other kinds of packaging and integration technologies. So we've really gotten a lot of benefit from working with the larger company. So let me get back to the topic at hand here of quantum computing. And you've seen much more kind of precise roadmaps from some of the companies that are building these large systems. We ourselves are not. We're really focused on some of the long-term scalability research with respect to quantum computing. But suffice to say that there's kind of, what we have now are these research grade systems, 50 qubits, and it's a very exciting time. Not that they can do anything a classical computer can't at this point. But this is where the rubber is really going to meet the road with respect to, being able to actually demonstrate and optimize error correction for real qubits with real error models. And of course, the very exciting quantum supremacy demos. And so when will this technology really start having an impact from an applications point of view for RTX's customers? We don't know. It could be at 1,000 qubits. It could be at 10,000 qubits. It will be somewhere in that range. I think once we get error correction, once we're able to get, say nominally 100 qubits to build a logical qubit, and you get on the order of 50 logical qubits, you start getting quantum supremacy with high fidelity logical qubits. And that's when those applications are going to start to come into play. And certainly by 10,000, I think, I think there's a lot of confidence that that will be the case. And I'll talk about a few applications of interest. But I think one of the interesting questions for us is, will we run into some of these scalability bottlenecks before or after that point? I think there's clear roadmaps we've seen from IBM and others to get to the 1,000 qubit scale. It seems like the engineering is there to do that, but there's some bigger questions to answer before we get an order of magnitude beyond that. And the question is, how big of a bottleneck will those be? How will that affect the timeline to application? Will the real commercial and DoD type applications come in before or after that bottleneck? So that's a kind of something that we're watching and thinking about very closely. and also working on some of those bottlenecks. So just to give you an idea of where we work in the stack, we work at multiple levels in the quantum computing stack. Some of the things are relevant, really right off the bat. Some of the control electronics that we've developed, the arbitrary pulse sequencer, is a way for research grade systems to get be able to control small test beds, and we've provided these for many collaborators over the years. Some of the software associated with that. We also have worked extensively on kind of the low latency digital feedback necessary for error correction, which is very relevant at this point in time. But I mentioned these longer term scalability issues, like at some point we'll want to have cryogenic digital electronics in the DR in order to do this control. We work on those digital cryogenic electronics, and we're very much interested in providing that as a way of scaling to larger systems. Similarly, we're very interested in the problem of transduction, because that's the way that we'll be able to connect quantum processors, multiple quantum processors, even over great distances via optical networking. And of course, you need to get from microwave to optical coherent transduction to do that. And our photonic integrated circuit technology is applicable to this, and we have some specific concepts we're thinking of there. And so finally, I wanted to conclude by just giving a little bit. I kind of talked about how we're kind of playing the role of contributing to quantum technology development, but of course, we're also very interested, RTX as a whole, in what those applications of quantum computing are going to be, and when they're going to come to fruition. So just to give you an idea of the things we have been thinking about, a lot of people here have talked about optimization, and that is the obvious one, right? It's ubiquitous. We work on these kinds of problems in non-quantum programs all the time. This is just a toy example, but there's multiple examples of optimally deploying multiple sensor resources. And how do you do that? How do you compute that optimal configuration? It's a problem that has a clear quantum advantage, and we're very interested in that application. Quantum machine learning, you've also heard about in other talks. Obviously, it's very relevant to many of our programs, and we expect the quantum advantage version of those to very much be relevant to our programs. Kind of turning to the more of the kind of physical modeling side, that has, of course, a lot of impact on DoD. So plasma modeling is very much of interest. Hypersonics modeling is very much of interest, and really the quantum algorithms that are relevant to that are able to solve differential equations more efficiently. We expect to have applications there. And then, of course, long term, very long term, we expect the kind of Shor's algorithm cryptography application to be quite impactful. But kind of ironically, despite the fact that that's been the thing that I think has obviously started the interest from the government funding early on and has sustained it over the decades, I think in the past 5 years, we really have seen a shift towards some of the other applications in the commercial and DoD side, and really a much broader spectrum of applications. And it looks from the numbers that those applications are actually going to be the ones that have the impact first. So I will stop there.
Thank you, Zach. That was terrific. And we're going to, just for the participants that have tuned in here, we will be taking questions after both speakers. I already introduced Dr. Brock. Darren, while we have a moment here, if you can just share screen, go ahead and load your presentation up. And so after Dr. Brock has given his presentation, then we'll go ahead and take questions. So I just wanted to remind people to go ahead and put your questions into the chat box, and we'll receive them here and we'll be ready. I see that someone has raised their hand already, so thank you for that. Dr. Brock, go ahead, please.
All right, well, thanks very much again for the opportunity to participate today. I am going to show you a little bit of marketing collateral that I grabbed, and I'm just going to talk. So feel free to look at the interesting graphics, but you know, I just wanted to make some basic points. You know, one of the things that is unique about aerospace and defense, as opposed to other industries, well, there's a couple of things. One is security. So both from a information security standpoint, and then also a life or safety critical sort of security, if you're making airplanes or you know, other things. And then the second piece that's a bit unique for aerospace and defense is the regulatory compliance framework. So when the U.S. government, or I suppose any government, is your primary customer, and they're using taxpayer money, they put a tremendous amount of compliance around how you perform and how you're going to build and deliver those systems. And of course, if it's, say, an airplane that has to fly over neighborhoods and carry people, well, then that's just going to be even more on that. So those are some unique things about our industry. So Lockheed Martin has been active in programs surrounding quantum technology now for probably close to 20 years. We work in quantum sensing, quantum communications, and computing. For the quantum sensing and comms work, we have our own R&D programs, both internally and externally funded, working from our business units. We also collaborate with universities, with small companies, with other large companies. In quantum computing, however, we do not have any sort of hardware development activities underway. What we do is collaborate with those organizations that do develop those technologies for access to hardware, and also to be able to track how that industry is growing. The main focus for Lockheed Martin in quantum computation is really in understanding how to formulate problems that allow you to tackle these sort of large combinatorial calculations. I should say that Lockheed Martin's technology agnostic, and so you know, we're well known for having a D-Wave access, and have continued to upgrade the access to that machine. I have a colleague who likes to say, what quantum computers do is interesting, but what you do with a quantum computer is important. And I think that's the standpoint that we take, is we're really interested in solving those sort of intractable problems, not just for performance, but also for sort of larger system level impacts, you know, affordability, systems that can be reused to do other things as well. So a few, I guess, observations that that sort of formulate the way we approach. So one is that all quantum systems are hybrid quantum classical systems. So you know, just by definition, if you're going to interact with a quantum system, it's hybrid. But in fact, you know, how you set up your problem, the infrastructure for that computation, whether it's on a platform or it's in a building, sort of all of the pathways for getting the information to constitute that problem, all of those will impact sort of how efficiently and how appropriately you can segment a problem to be utilized together with a quantum resource. Another sort of maybe central tenet, you know, we talk about application effectiveness and we talk about system impact. And so in terms of application effectiveness, can this technology do a particular function to the level of precision that's required? but then at the system impact level, is it addressing a bottleneck in the system? Or is there if that's not the bottleneck, you're not going to get an overall benefit, even though your particular capability may be faster. I think it's fair to say that Lockheed Martin is we have access to experts in quantum computing resources. The thing that I think we're more interested in is access to people who are experts in high value, very difficult computations. In other words, folks who are experts at the bleeding edge of doing what they do today that need to take that to an even higher level because it's important. And so I'll tell a real short story here about a colleague of mine, Ray Hill, who works at our Advanced Technology Laboratory in Cherry Hill, New Jersey now. So Ray is a mathematician by training, and he's not particularly a quantum expert in anything, but he knows a lot about encoding radar waveforms. Most people know, but as a brief aside, in a radar system, you have a radio wave that you send out and it bounces back, and you typically will modulate that with a very long pseudorandom binary sequence. As the wave comes back, you're able to basically correlate against that and take that information. And there are a bunch of features you would prefer to have about that long pseudorandom binary sequence. You'd like it to be as long as possible, so it makes it as hard as possible for someone else to kind of pick out what that modulation is. And then you'd also like it to have some particular characteristics that have to do with the sort of peak side lobe shaping in frequency space. So Ray had supported this for some of the shipboard, the Navy radar systems, very familiar with this. And the way the US Navy gets these codes, they come from the Naval Research Lab, where they're computed on a supercomputer. And there are a finite number of them. And so they're a precious commodity. They're expensive to compute. And you need to change them frequently, but obviously you don't want to just use them all up. So with that preamble, when we were working with one of the original D waves, so Ray Hill set out to see, could we find a more efficient way to calculate those pseudorandom binary sequences that have these particular peak side lobe behavior. And what he ended up doing was something that I thought, at least from my perspective, was very non-obvious. What he ended up doing was using a classical genetic algorithm. A genetic algorithm, you typically do lots of random restarts, and then as an ensemble together, let the calculation show you the global minimum. So he did that, but he used the D-Wave resource to basically restrict the set of possible resources so that he had a more, let's call it, optimum restart point, so that his classical genetic algorithm would converge more quickly. And as a result, he was able to do his calculation for a lot less wall clock time than he would have had, simply doing it classically. And so I was really impressed with this. The quantum resource is an extra tool in the toolbox. It's not I'm going to substitute my calculation from doing it, on a supercomputer to doing it over on this system over there. I'll say as an aside, if you can afford a separate big supercomputer system just to do one thing for you, you get all the codes you want that way. But in fact, that is a restriction there. So I guess the takeaway from that was that that setting up the problem, formulating the problem can be just as important as the physical system that you're using to store and process the quantum information. And as we go forward into kind of the next big technology challenges for defense and aerospace, I think that an area that is really important to emphasize is being able to put into the hands of people who are experts in other fields access to quantum resources. And it's not a trivial thing, because there are, we don't realize how closely existing problems are formulated to fit the sorts of traditional solutions that we've used. Richard Carp, back in the 1970s, it has this famous paper where he kind of called out all these, I think it was 21 classes of combinatorial problems, 21 NP complete types of problems. And for most of those today, there are, if you put some restrictions on some of those individual classes, you can get reasonably efficient approximations to them. And so those are used. In other words, people structure their problem to fit into one of those restriction cases. And so in some sense, they have sort of pre-categorized their computation with the assumption that it will be done in a traditional classical manner. And so I think kind of breaking out of that, that mindset that that you need to step back and look at a larger perspective. And this goes from, there's a whole host of different sort of combinatorial problems, anything to do with, say, moving ground target indicators or other radars, things where you have frames of sensor data coming in, and you need to associate sensor data with tracks. There's way more information coming in than can be processed. And so, fortunately, we know a lot more about the situation. We can restrict and narrow that case. We know airplanes don't turn 90 degrees, they don't accelerate to 5,000 miles an hour. And so you're able to kind of reduce that search space. But as we get more UAVs, as we get more multi-domain operations, as there may be additional sort of countermeasures and spoofing to deal with, those assumptions may be challenged, and may be challenged at a time frame that is difficult to keep up with in that traditional way. So I guess to summarize my comments, I'd say that Lockheed Martin doesn't have any plans to make and market quantum computers, at least at the moment. We are technology agnostic, and we're sort of very mission value, mission benefit focused, where you have to fit into and connect with an existing infrastructure. Reformulating the computational problem to use a quantum resource is not transparent. So let me leave it there for now, and we'll have some time for questions. So thanks.
Terrific, thank you. Darren, that was terrific. We have a number of questions that have come in. And so what I'd like to do is address a couple of those. The first one, I think, was to clarify something, Zach, that you said, and you used a phrase, the scale of critical need. How would you, can you clarify that and what you meant by the scale of critical need?
Yeah, so what I attempted to do there was list several technologies we were developing and when they would be required to remove a bottleneck to a quantum computing system at that point in time. So for example, cryogenic electronics could be necessary once we get above 1,000 qubits because of some of the packaging and wiring constraints. The transduction technology will probably become relevant once we get to multiple tens of thousands, because at that point we will need to network quantum computers together in order to get keep them quantum coherent and get their full power. There are some other things I put that were problems even near term, like verification and validation. Those kinds of things hit you when you get even to 5 qubits, which is some of the near-term scalability challenges.
Okay, so that clarifies it. In fact, I had another question that related to this. You displayed what in your presentation, Zach, what would be a number of enabling technologies that RTX is working on: control electronics, low latency feedback, cryogenics, some microwave text. How does Raytheon plan on engaging with those technologies in the quantum community? Though you're not going to become a manufacturer of enabling techs, or are you going to license these, or how will you bring these into fruition?
Yeah, so I mean, what we tend to do is to build at least, BBN and many parts of Raytheon. What we tend to do is build advanced prototypes for specific customers. Let me think of some examples. So control electronics and low latency processing, and sometimes these tend to be on the classified side. There'll be a particular customer that has a particular kind of system need, and we would be developing kind of that system prototype. And to your point, we're not going to necessarily own all the hardware. We'll have some of the hardware expertise, and we tend to specialize in hardware that we can't get outside. But if we can do something at a foundry, we'll often use that foundry and integrate it with other technologies that we need to develop internally for those specialized systems.
Okay,
so I mean, the point being that lots of military and DoD customers have very specific requirements that aren't necessarily viable for commercial products.
Right, exactly. Okay, very good. Let me develop a couple of, formulate a question based on a couple of these from the audience. I want to put a fine point on applications. Both of you mentioned a number of applications, and you both talked about where those could be, and they're kind of first order applications that would have direct impact on mission systems, and then there were sort of second order applications like modeling materials or computational fluid dynamics that could in fact impact the design of a platform rather than be on board that platform. For both of you, and Darren, you mentioned combinatorial problems and examples of intractable problems. For both of you, can you just freeze in our minds as the audience one problem each, one category of problem each, where you would expect near term or midterm or at least first impact for the Department of Defense and for the aerospace industry? One example from each of you, Zach.
Yeah, I mean, I would agree with Darren about combinatorial, and specifically I mentioned, for example, sensor resource optimization. There's so many programs that we have that are about logistics, for military planners and other customers on the intelligence community as well. So just the ubiquitousness of that particular problem, that optimization, over multiple parameters, I think gives it a very high chance of having the nearest term impact. We also have a very good quantitative understanding of the advantage. the question is, it is a polynomial speedup, and the big open question is polynomial speedup really going to be enough? You know, is there, it might be that the window of advantage when you're basically you're polynomially improving an exponentially difficult problem that helps you at certain scales. Will it help you at critical scales, or will it be just kind of this small window of advantage, and who really cares longer term? So it's not a slam dunk, but it's certainly a very well-defined, very ubiquitous problem where we know there's a quantum advantage, and certainly I'm most interested in that.
Yeah, great. Okay, thanks. Darren, let me throw that same question over to you. Just again, to freeze in our audience's mind, what would be the one problem or category of problems you would expect there would be a first motion in your retinue of intractable problem examples?
Well, certainly one of the areas that would make a tremendous impact, and Zach mentioned this, is software verification and validation. You know, one of those marketing charts that I had up there, I think had a F-35 picture on it. So you know, the amount of software that runs on F-35 is awe-inspiring. And in order to get an airworthiness certificate for that, or for that matter, any aircraft, you have to prove to the regulatory body that there's something like a 1 in 10 to the 6th chance of a you know, real life critical situation. And if you go down to Fort Worth, Texas, where they have the F-35 assembly line, there's a whole floor of a building where they have an F-35 that's sort of completely taken apart into all of its pieces, and they are essentially trying to exercise all of the possible input states and register configurations to basically go through and prove that this system software is reliable. And of course they can't. They can only look at a small fraction of those. And you know, this is part of the reason that you have you know, secondary redundant systems and tertiary redundant systems, because then you can get sort of the probability down significantly smaller without having to actually cover everyone there. So I think there's area there. F-35 is an example, but sort of for any modern complex physical electromechanical system, that verification validation. Now, I will also say that the challenge with that is that, you know, to formulate that problem, you need to have your requirements basically defined in formal methods. And requirements for complex software tend to be formulated in contracts, in Excel charts, in code comments. And so again, that's the, you know, sort of Zach mentioned, you know, 5 qubits sufficient to already start to do some stuff in that area. But it's, so application effectiveness, thumbs up. System impact, at the moment, we're not there yet.
Very interesting. That is very good information. So you respectively mentioned sensor optimization, logistics, and whether or not the speed would be sufficient and compelling. And Darren, you mentioned software V&V, and perhaps even the elimination of redundant systems would be one benefit of that, as well as just whether code operates smoothly. Hopefully, those are 2 crystal clear takeaways people can grab from this presentation. And now I have a follow-on question. How are we doing in each of those areas? How is your main customer, the Department of Defense, doing in promoting the utilization of quantum in either of those 2 areas? And what are the hurdles in getting applications forwarded in either of those areas? Darren, let me ask you first.
I think there's very strong support from the U.S. defense and intelligence communities for the utilization of quantum resources as an additional tool in the toolbox to do some of the really hard missions they have in an increasingly both complicated world and increasingly, I guess, with pace of change, updating very much more quickly than it was sort of in the Cold War days. I say that from a sort of a generic technology point of view. In terms of actual adoption of, okay, we're going to go use this. The what's the right way to put it? If you are addressing a real problem that your customer has, then there's not, you can get the funding that you need, you can get the time frame that you need. If you're addressing technology that helps problems like a class of problems, much harder. So if you are responding to an unmet need with your sort of innovation, the spigots just open right up.
Great. Zach, how is the Department of Defense and the government in general doing in quantum adoption, particularly in the areas you mentioned? And also, what do you think any internal hurdles for them might be?
Yeah, I mean, certainly over the decades, the intelligence community has been very interested in technology and has been supporting its development. They have an obvious killer app that's been driving that. On the DoD side, it's been a bit more uneven, but I think, there was a lot of progress in the field technologically kind of from 2005 to 2015 that's led to the floodgates of commercial money coming in. And I think the DoD has kind of followed that trend. So now we're seeing kind of more consistent support for quantum computing and quantum technology in general on the DoD side, and a lot more kind of acceptance that it will be important. We're seeing, DARPA, ONISC, and other kinds of programs popping up more. But I would absolutely agree with Darren about the long-term hurdles. If you're not, different agencies have different levels of conservatism, and a lot of times your technology we have technology that we are trying to transition now that's a lot less crazy than quantum computing, a lot more further along TRL wise, and a lot less speculative. And even there, because it requires a rethinking of the system, a rethinking of the architecture, there's certain customers that just can't swallow that. So there's really it could really be a struggle, especially with certain customers, if, like Darren said, if you're not meeting a very, very specific, solving a very, very specific problem. So I do see longer term some challenges there, as far as kind of getting the things that quantum can offer into, what we call requirements, which is often what's needed to move things along.
Great, thank you. We have just a couple of minutes left here in the waning moments of the panel. I wanted to give each of you 30 seconds or a minute to just perhaps put to voice something you would like to see developed in the quantum computing ecosystem. If you could wave a magic wand, what would make your jobs easier? What would be a breakthrough for you? Just anything that you feel that would make a real advance for the quantum industry today. Each of you maybe take a minute and lay that out. Let me start with Darren first. Darren?
Yeah, so there are numerous technologies under development that I think have tremendous promise, but perhaps a factor that crosses over those is if there was a sort of a way to get more of the quantum resource into the hands of experts who are experts in other areas. And that comes all the way from sort of physically integrating into a system for, as I talked about before, formulating problems. There does tend to be I think there are some good software level abstractions, but in terms of, how does this work? And then somebody goes to the board and, you derive what this is. And then suddenly you're looking at glazed eyes. There is a certain, there's an upfront cost to thinking in terms of quantum information representation. And I don't mean standards, but ways to kind of bound a subsystem so that it has a set of defined interfaces and can be treated as not an oversimplified black box, but a well-defined black box. I think that will get more people contributing to the sort of the use and also giving feedback to help guide quantum computation as a resource in a larger hybrid system.
Okay, so if I heard you correctly, Darren, it would be more what Jay Lowell of Boeing called pie-shaped engineers earlier today. like the letters pi, they have two legs, one in an area of domain expertise, the other in the area of quantum expertise, and then the bridge between them. And he talked about that. I thought that was amusing. Very good. Zach, let me give you a minute in closing here to express what would you do if you had a magic wand? What would it be? A technology, more funding, a policy, more people, as Darren stated?
Yeah, so I would definitely, relevant to the session this morning, say that workforce is a big issue that we think about a lot. And if we had more people trained in quantum technologies, what we've really been focusing on in the QEDC, for example, is people that are trained for example, at a master's level. We don't need just PhDs, but we're able to put smart master's engineers to work. And if they had some quantum training coming in, I think that would really increase the resources available to make progress in the field. So that would be one. And the other is, I think, some early victories, and those early victories might really come from sensing. We have some prototypes that have advantage. If we can get adoption of some of those, I think it will help the overall technology development. It will help the overall credibility of quantum for eventual applications in computing and entanglement distribution, which could be a little further down the line. And that was a big focus of some of the work, some of the discussions I've seen for sure in the defense industry.
Very good. Well, thank you, Zach. And with that, I'm going to adjourn the session with a word of thanks to both of you. Dr. Dutton, Dr. Brock, thank you so much for your enlightening presentations today and your commentary and addressing the questions. I'm quite certain people walked away from this session with a good deal of knowledge and have benefited from your expertise. Amit and Lawrence, thank you very much for hosting just a wonderful conference. I look forward to tomorrow's session as well. And thank you all very, very much. Take care. Bye-bye.
Thanks for having us.